Hi, welcome back to a new lecture from the course Computer Vision from Scratch. Today, we'll be learning about convolution layers, pooling, and AlexNet. If you don't know any of these terms, don't worry. We'll be approaching this as if we are all complete beginners. We have spent some time on convolution filters in one of the earlier lectures at the start of this course. However, we did not look at convolution from the context of deep neural network layers, where in reality you have multiple convolution operations that are being applied on your data set one after the other. So we'll be looking at convolution as an individual kernel or individual filter that is being applied on an image. We'll also look at convolution as a stack of operations. Then we'll spend some time on pooling, such as max pooling, which is a very famous operation used in many deep neural networks. And towards the end of this lecture, we'll be also implementing AlexNet, which is one of the most popular deep neural networks. And AlexNet had revolutionized the way deep learning was implemented for various tasks, especially for computer vision related tasks. So this is going to be a very important lecture, and I'm so excited to have you all here. So with that, let's get into the lecture. So before we get into the lecture, as always, let us all remind ourselves that starting a course is easy, but finishing is not. And if you have reached until this point, you have already done a fantastic job. You have covered a good fraction of the course already. But let's remind ourselves to finish the course because there is a reason why we started. So have a pledge, keep it for yourself. If you want to make yourself accountable, have a friend or whoever is learning the course along with you, keep each other accountable, or even put a comment publicly so that you are publicly held accountable. But at the end of the day, this is all about internal motivation and discipline. But I hope that you can carry forward this course along with me till the end of the last lecture. So at the end of today's lecture, we will understand what exactly is a convolution filter, how does it operate on an image, what does it do. We will see the implementation of convolution, plus after that also pooling, especially max pooling. We will spend a little bit of time on AlexNet. AlexNet is a historic milestone in the machine learning, deep learning evolution, because AlexNet completely changed the way deep learning was implemented for tasks like computer vision related tasks. So we will understand the architecture of AlexNet in detail. But not just that, we'll also implement AlexNet for our dataset that we have been following throughout this course, which is the 5 flowers dataset. So you will see what kind of results can we get by using AlexNet. We'll be using pre-trained AlexNet because training from scratch will take a lot of time and it's unnecessary. So just like how we learned from the transfer learning lecture, we'll be using pre-trained AlexNet, but we'll see what kind of results can we get, meaning what kind of training accuracy and validation accuracy can we get by implementing AlexNet on the 5 flowers dataset. So with that, let's look at what is convolution operation. Before we go into convolution, I think a small recap of what exactly are we doing and what did we do so far. I think that will be very helpful to all of you. So why are we learning all of this? What exactly are we doing? So just to remind you, we are looking at 5 flowers dataset. So we have daisy, dandelion, roses, sunflowers, tulips. So it's a dataset consisting of thousands of images, and each image belongs to one of these 5 categories. So we are trying to build a 5-class classifier. So what did we do? We started with a linear model. And what is a linear model? We converted the RGB images like this into a fully flat layer. So we flattened the image with RGB like that, repeating. And then we had a fully connected connection to the final output layer, which was a 5-node layer. And when we trained this neural network, and you can already see that this is not even a neural network. This is just a linear model, right? Because there is no hidden layer. There is nothing special going on here. With this linear model, we managed to get like 40-45% accuracy. We had no activation. We simply had softmax in the last layer. But that was just to convert the final output into a probability distribution. So 40-45% was the accuracy. Loss was 10-20. After this, we thought, okay, maybe we need a hidden layer to make our model better, because if you don't have hidden layer, how can the model learn a lot of complex features or complex things that are happening in these images, right? So we added one additional hidden layer with 128 nodes. But this time we did not go with a linear model. We had ReLU, rectified linear unit activation function. We thought this might improve the accuracy by a good fraction, but it did not happen. Accuracy stayed, like when I say accuracy, I mean primarily training accuracy. It was in this range, 40 to 45%. Validation accuracy was also somewhere in that range, not tremendously high. But interestingly, loss decreased by an order of magnitude. Loss was 1 to 2% instead of 10 to 20%. So the number of images that were getting classified accurately was still the same, which is why accuracy did not change. But the confidence with which correct classifications were being made, that was better. So that's why loss decreased. Then we thought, okay, this is also not very good. Can we do something else? Maybe we can prevent overfitting, which may be happening, because we had noticed that in some cases we were getting 55% training accuracy and like 35-40% validation accuracy. So some kind of overfitting was going on, and this was getting more pronounced as we increase the number of epochs. So we thought, okay, we have to implement sort of overfit prevention techniques. So we had regularization, L1, L2 regularization. We had patch normalization. We had dropout. We also had early stopping. So in regularization, you prevent the weights from blowing up. You kind of restrict the weights, the magnitude of the weights. In batch normalization, you make sure that your data set is centered around mean equal to 0 and standard deviation equal to 1. In dropout, we kind of switch off certain nodes in the neural network layers with a certain probability. So if the probability is 0.5, there is a half or 50% chance that a node will be inactive in that particular training. And we also implemented early stopping. So epochs, if the epoch continuously decreases for, let's say, if accuracy continuously decreases for 2 epochs, then you can stop training from that point onwards. So this is early stopping. It did not increase our accuracy tremendously. Our validation accuracy was 50 to 60%. So not a great improvement. Loss was still 1 to 2%. But training accuracy, we were able to take to maybe 80% in some cases. So, but validation accuracy was still 50 to 60%. Not so great, right? It was not the best because this is a 5-class classification. The worst possible classification accuracy is 20% in the case of random guessing. So 50 to 60% is not that incredible, considering the fact that we have hidden layer, we have non-linearity, we have all these regularization, batch normalization, etc. Which is why we realized that we have to do transfer learning. So in the previous lecture, we spent some time on transfer learning, where we used an already trained neural network. So this neural network was already trained on ImageNet dataset, and this neural network had not random weights and biases. It had pre-trained weights and biases. So with this pre-trained neural network, we added an additional final layer, which had 5 nodes. And then we allowed the neural network to train on the 5-flower dataset. And with that, we were able to get validation accuracy of 80%. And in fact, training accuracy, we even managed to get about 100%. So this was the biggest jump, because we initially struggled at 40 to 45% validation accuracy, and eventually we almost doubled. Our training accuracy reached almost 100%, validation accuracy 80. It could reach to even to 83%. So this was great. Not the best, but very, very good improvement. So today's lecture will make you even more happy for obvious reasons, because at the end of today's lecture, you will see how the accuracy can even be made better. So today also we'll be looking at transfer learning, but we'll spend some time on convolution, pooling, and at the end AlexNet. But AlexNet we'll be using as a pre-trained AlexNet model, so that we can transfer some of the learnings from its previous dataset on whatever dataset this AlexNet was trained on. So with that, let's get into the basic aspects of today's lecture. I hope this recap gives you a very good perspective of what exactly are we trying to do. So what exactly is convolution? You can think of convolution as if you are performing a moving dot product of one small matrix on top of another big matrix. The small matrix is called as the convolution filter or a kernel. The big matrix could be thought of as the pixel values of your image. So this filter will be applied over your image to produce a resulting image, right? So there is a GIF that I have added here at the top of this lecture. So just let me play it so that you can see convolution operation as an animation. So if you take a look at this animation, you will see how convolution happens, where this 3 by 3 matrix that is moving over the blue 5 by 5 image with a padding of just 1 pixels. It is resulting in another new matrix over here, this greenish blue kind of matrix, and that is the result of convolution. So convolution as an animation occurs like this, but mathematically, let's see how exactly it works. So these are some examples of convolutions, and you will understand the intuition behind convolution just by applying this onto an image, right? So here I have a sample image. What I'm going to do is, let me first take a screenshot of this image, and let's apply convolution on top of this image. So I'm taking a screenshot, and then there is this website. The link of the website I'll share with you, setosa.io. On this website, we can choose the image on top of which we want to apply the convolution. So let me do that. Let me load so this was the image of which we took the screenshot. And then what we are going to do is we'll apply a filter like 1, 2, 1, 0, 0, 0, minus 1, minus 2, minus 1. All right. So 1, 2, 1, 0, 0, 0, minus 1, minus 2, minus 1. And look at what happened. All the bottom edges in the image is now becoming highlighted. So there are a few things to note. What exactly are we doing here? What is happening is this image is consisting of a bunch of pixels, right? And this convolution filter will move over this image. And whenever this convolution filter is on top of another set of 9 pixels, because this is a 3 by 3 filter, right? So at any given point of time, this 3 by 3 filter will be on top of another subset of pixels of 3 by 3 size. That will result in a 1 by 1 pixel value. So let's write it down here. So let's say you have a matrix like this, and if this is your original image, it has bunch of pixel values. And for simplicity, let's say my convolution layer is something like 2 by 2 convolution filter. Then these pixels in my image might have different numbers. So let's say this is 20, this is 1, 0, 15, 200, 35, 7, etc. I'll add a few more, 9, 91, 100. And let's say my filter is like this, 0, 1, minus 1, 0. Now, how do you calculate the result when this filter, let's say this filter is now overlapping with, so what I'm going to do is like I'm grouping this filter into just one single thing like this, and maybe I can provide a different color. So let's say my filter is over here initially. Then this 2 by 2 filter is on top of another subset of pixels of size 2 by 2. And the result will be 0 times 20 plus 1 times 1 plus 35 times minus 1 plus 7 times 0. And the result of that will be 1 plus minus 35, which will be minus 34. So the result of the convolution of layer, this convolution filter applied on top of these 4 pixels is minus 34. Then what happens? Then this will move. And when this moves, this 2 by 2 filter is on top of another subset of 2 by 2 pixels. And this time the result would be 1 times 1 plus minus 1 times, plus 1 times 0 plus minus 1 times 7 plus 8 times 0. So the result of that would be 0 minus 7, and that will be minus 7 itself. And like that, you can calculate the pixel values of the resulting image, and the dimension of the resulting image will depend on whether you are adding a padding meaning an extra thickness of let's say pixels of some value, or it will also depend on whether your stride, whether from here you are jumping only 1 or whether you're jumping like 1, 2. whether your stride is 1 or 2 or 3, whatever your stride is, and whatever your padding is, and also the kernel size. So here the kernel size is 2 by 2. If the kernel size was bigger, that also will influence the size of the resulting image or resulting matrix. But basically, this is how at a individual kernel and the subset of the image level, this is how the convolution operation works. Now with that, here we applied a particular convolution filter. The name of this filter is called as Sobel filter. And in this particular case, this Sobel filter is being used for bottom edge detection. And as you can see, when you are applying this 1, 2, 1, 0, 0, 0, minus 1, minus 2, minus 1, this bottom edge is being highlighted. Here is one way to visualize this convolution filter. So imagine this kernel like a light source. And this light source has a certain type of directionality. And the way you can visualize is, it's as if light ray is going from negative numbers to positive numbers. So a light ray, you can imagine 3 light rays to be going from this minus 1 to 1, minus 2 to 2, and minus 1 to 1. So the light ray is going from bottom to top in this direction. Now, the original image that you had, you imagine those shapes to be projecting outside the plane of the paper. So you have a cylinder projecting outside the plane of the paper. You had I think this was, one of them was a triangle, one of them was a diamond, and one of them was a square. So all of them imagine to be shapes projecting outside the plane of the paper. And then if you had such a shape, and if you had a light going from bottom to top, you'll be illuminating the bottom side of those shapes, right? And that's exactly what's happening here when you apply the filter on this particular image. Now, with this intuition, you can easily visualize what happens if you change the shape of this kernel. So let's say I change this from minus 1, minus 2, minus 1, and this is changed to 1, 2, 1. Then it's as if light ray is coming from top to bottom, which means the top sides of the projections will be illuminated. And that's what you see here when you modify the original image using the filter. You can also implement a light source going from inside to outside. So how would you do that? Inside has to be some negative number. So let's say this is minus 4. And let's say this is 0. This is 1. This is 1. This is 0. And this is 1, 1. Now you can imagine there is a light source at the center, and it's sending light rays in all the 4 directions, which means this time you have to imagine like a hollow shape. So hollow cylinder, hollow square, hollow triangle, or hollow diamond, in which light source is placed inside, which means all the outside edges will get illuminated. Imagine like a hollow shapes projecting outside and light source is inside, and the light is going outside. So then it illuminates all the edges. So, and then you can do the same thing. Like if you had minus 1 here, and let's say 2, 2, then let's say this is 0. This should be in fact minus 2, minus 2. And let's say this is 0, 0, 0. And then this is 1, 2, 2. So you can predict the direction of the light source. So here it's negative numbers and here it's positive numbers. So light is going from the top left corner to the bottom right corner. And you can see that accordingly in these figures, if you imagine projection outside, the top left corners are getting illuminated as if light is coming from that side. So this is a very good intuition that you can build to understand what each filter might be doing. Here, one interesting thing that you can note is the sum of the numbers in this filter is 0. So, but if the sum was 1, it means the overall average intensity will be maintained. But here, since it is 0, the average intensity will be reduced compared to what it was there in the original image. Because here, whatever pixel values this filter encounters, the net value will be net summation. If you have a completely bright image of, let's say, 255, 255, 255, etc., then that image will completely become black, because all the negative numbers here will cancel all the positive numbers. So this is an intuition of filters, how filters work. But there are many different type of filters, some for identifying edges, some for identifying textures, some for identifying even more intricate patterns. And in many cases, deep neural network uses various type of filters but you don't define filters manually like how we did here. Instead, you make the filters, the values inside these filters a learnable parameter. So this is exactly how deep neural networks work. So now I think when you look at these 4 filters, you will have a better intuition here. Look at the filter, negative numbers at the bottom, positive numbers at the top, which means it's as if light ray is going from bottom to top. And you can see that the bottom edges are illuminated. Here, it's a slanted edge detection. So there are positive numbers in the top left corner, bottom right corner has negative numbers. So light ray is going from bottom right to top left. And you can see that the bottom right edges are getting illuminated and so on. And outline detection means the light has to go from either inside to outside, or light can also come from outside to inside. In that case also you will get edges. Let's actually do that. So if light is coming from outside to inside, so let's say this is -2, -2, -2. And this is also -2, -2. Actually, I don't need this. This can be, corners can be zeros. And the center value should be the sum of all of this, which is 8 in this case. Here also you can see that this is as if light source, there is a uniform ring light outside, and that light source is bringing light to the center, and that will again illuminate the edges of all the shapes. So you can see that all the outlines of these different shapes are getting illuminated. So this is how filters work in principle. But now let's implement a simple filter using code in Google Colab. So before we open Colab, let's see what exactly are we doing here. Here we are using this color library from scikit-image. So that is skimage. And the filter that we are defining is such that it goes like, it's as if there is a light ray going from top to bottom. So -1, -1, -1 at the top, zeros in the center, 1, 1, 1 at the bottom. And then we'll use this as a convolution filter on our coffee image. So let's actually copy the code and let's run it. So open Colab, colab.research.google.com. And we can name this as the code file as a simple convolution operation implementation. Simple. This is not yet convolutional neural network. There is no neural network here. It's just convolution operation. So let's paste the code here and let's run it to see first what kind of action this filter does on top of the image. And after that, we can try changing the values inside this filter. So now here we have the result. Original image is this coffee cup. And after convolution, it looks like this. And filter is -1, -1, -1, 1, 1, 1 at the bottom. If you now think in terms of the light ray analogy, you can see how the principle is working here. And often the analogy of the direction of light depends on what is your image. In the previous image that we were looking at, image was in white color and the background was in dark color. If this flips, we may have to look at light source in an opposite way. Maybe the source of light might be at the positive values of the kernel and the destination would be towards the negative numbers in the kernel. But the basic principle still applies. In general, here you can see horizontal edges will be illuminated rather than vertical edges. And you can see that in this coffee cup, this is like a sort of like a horizontal edge. This is also sort of like a horizontal edge. Now, if we want to eliminate another set of edges, we can make this -1, -1, -1. This can be zeros, and then this can be +1, +1, +1. And if we run this code, another set of edges will be now illuminated, and this should hopefully be the vertical edges. So now you can see that this edge is like a vertical edge. This is also like a vertical edge because now the light is going in horizontal direction. And because of that reason, different sets of edges are now getting illuminated. And if you want to not discriminate horizontal or vertical edge, if you want all sorts of edges, then what you can do is keep these as zeros and corners as -1. And the center value could be, let's say, 4, which means the total sum will be 0, 4, and there are 4 negative ones. And now all edges will be illuminated, but the brightness, as you can see, has reduced. That is because the sum here is 0. If you want sum here to be 1, then overall brightness will not decrease. So you can keep the center value to be 5. And then if you run this, you will see a brighter image. See, this image is brighter than earlier version, but it will also illuminate the edges. So actually what you can do here is you can increase this a bit more. Then you will get an even brighter image with a little bit of edge detection. So this image is now a bit sharper. You can increase this value even further, and you will get better and better and more brightly edge illuminated images. I'll share this code with you. You can play with it. There are many types of filters. You can manually define the filter, but there are also functions which allow you to call filters that you want. So this is a basic convolution operation. And in a convolutional neural network, our goal, or the neural network's goal, is to identify different features from the image, right? Edges are not the only features. There are other textures. There are maybe color patterns, and so many things make up. There might be geometric features, like if you have a cat versus a dog, the cat may have sharp ears, whereas dog may have flappy ears. So these are all features which different types of filters, convolution filters, may detect. So this is the basic idea of why convolutional neural network requires filters. Now what we'll do is, let us first, before we implement CNN, let us first look at the convolution, stacking of convolution operation from a dimensionality perspective. Meaning, if we have a certain dimension image, RGB image with, let's say, 224 by 224 dimension, and if we apply a certain type of filter on this, a convolution filter on this, what does it result in? Does it change the dimensionality, or is the dimensionality going to be preserved? Does the Z stack, instead of 3 channels, will the number of channels increase? So let's ask all of these questions, and let's try to compute the total number of learnable parameters, because we discussed that in a convolutional neural network, we don't define filters manually. The values inside the filters are weights, which is a learnable parameter. We just define the size of those filters, which will be a hyperparameter. But the values inside these filters are parameters which are learned during the training process. So let's see now how many weight parameters will be there in a neural network if you are applying a certain type of filter to an image. So let's say this is the input image dimension. It has certain number of length and breadth. So let's say this is a 224 by 224 by 3 image. In fact, here we can count it. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 10 by 10 image dimension. But there are 3 channels, RGB channels, right? And this is like a tensor which has 3 dimensions. So the number of channels can be 3 or 5 or whatever. So now on this image, let's say we are applying 5 separate filters, 5 filters independently, and the filter size of each filter is 4 by 4 by 3. So we have a 4 by 4 filter, but that is repeated 3 times. So same 4 by 4 filter has 3 stacks. So 4 by 4 by 3. And then this 4 by 4 by 3 filter will act on this 10 by 10 by 3 image to produce a new stack. But then there are 5 such filters. So instead of just a 4 by 4 by 3 filter, you have a 4 by 4 by 3. This will repeat 5 times. So now you have 5 convolution filters, and each filter has a dimension of 4 by 4 by 3. In the 2 dimensions XY plane, the dimension is 4 by 4, but then multiplied by 3 comes because there are RGB channels. So this will result in a dimension as shown here. So the resulting dimension is you have 10 by 10 by 5, right? So if this is the input, and if this is the filter, in fact filters, there are multiple filters, the resulting output is 10 by 10 by 5. So here, how many learnable parameters are there? First of all, what are the learnable parameters? The learnable parameters are whatever values are there inside these filters, which will allow us to extract whatever is useful for us to make a good prediction. So now this is the output. In this case, you can think of output as a different representation of the input image. So the input image is now represented in a different format by convolving through these filters. All right. So how many learnable parameters are there? The number of learnable parameters will depend on number of parameters, the total number of parameters you have in the filters. So look at individual filter. As you see in this image, it is 4 by 4 by 3. So every single filter will have 4 by 4 by 3 number of parameters. And what is this? 16 multiplied by 3, that is 48. But like that, there are 5 independent filters. So this is the filter number 1, filter number 2, filter number 3, 4, 5. And all of these 5 filters will act on our input to produce something that you see here. So you will have to multiply 48 by 5, which is 240. So in this particular case, you have totally 240 learnable parameters. So that is what I have mentioned here. And these learnable parameters will be values that will get changed during the training process of the neural network. So this is an example of how a single convolution operation applies on top of a real RGB image. In CNN, however, instead of a single convolution, there are stacks of convolutions. Each convolution filter will get trained such that it can detect some particular feature, and each filter will detect a separate feature. Now, what are these features or what are these patterns? There could be the circularity, there could be corners, the geometric shapes, etc. So originally, your image will be simply pixels. These pixels can be utilized, the value of these pixels can be utilized to identify edges. The edges themselves may have textures. Textures plus edges will help you identify parts of objects like, whiskers or ears of a cat or whiskers of a cat, or if it's an elephant, the tusk. And then these parts will ultimately allow you to identify objects. And this can be used for segmenting images, or this can be used for classifying images. Various computer vision operations can be performed. The real heart of computer vision you can think of as convolution operation, because convolution operation allows you to get data from the images which are originally just in the form of pixel values. Now, if you want to implement a simple convolution stack in Keras, it's very simple because, see, usually in Keras, we define different layers as models.sequential, and then we can say input layer, hidden layer 1, hidden layer 2, etc. up to output layer. Here, what you see is you have an input layer of shape 128 by 128 by 3. So this is the input image dimension. 128, 128 is the resolution. 3 is the number of channels. And then you have a convolution filter. And you can see the definition of the convolution filter size here. And 16 is the number of filters that we are applying. 3 by 3 is the filter size. So here, the resulting dimension from this will be 128, 128, 3 will be converted to 128, 128, 16 if you have appropriate padding. If you don't have padding, the size of the filter will be reduced to 126, 126, 16. Because if you have stride equal to 1 and if you have no padding, it means from the left hand side and right hand side, one pixel each will be removed. From the top side and from the bottom side, 1 pixel each will be removed. So instead of 128, 128, 16, you will have 126, 126, 16. If you are using a 3 by 3 filter with no padding, with stride equal to 1. But if you have 3 by 3 filter with padding and with padding equal to 1 and with stride equal to 1, then you will get same dimension 128, 128. But the number of channels will not be 3, number of channels will be 16. And then that will be converted to 128, 128, 32. And then that will be converted to 128, 128, 64. Assuming there is padding equal to 1 and stride equal to 1. But in between each layers, we are also applying an activation function like ReLU. So this ReLU will ensure that there are no negative numbers in the pixel values. So everything that is output at the end of every single layer will be just positive numbers. So this is how the model look like. And now just look at this image, and using this image, we can try to understand stack of convolutions, right? So the input here is 10 by 10 by 4. Yeah, I think this is 10 by 10 by 4. On this 10 by 10 by 4, we are applying 3 by 3 by 6. So there are 6 3 by 3 convolution applied on 6 different channels. So as a result, our image will become 10 by 6. So previously, what had happened to our image? It was 128 by 128 by 3. On this, we were applying 3 by 3 filter, but there were 16 channels. So the dimension became 128, 128, 16, then 128, 128, 32, like that. Here, the original image dimension, just think of this as a tensor, because when you think of 4-dimensional image, you can think of different color channels. If it's like a fluorescent image, there are different fluorescent wavelengths. So here you have 10 by 10 by 4 image that on that you are applying a 3 by 3 convolution filter, but totally there are 6 dimensions, like 6. It's as if there are 6 filters, which means your resultant dimension will be 10 by 10 by 6 instead of 10 by 10 by 4. Now let's say on top of this you are applying a 2 by 2 convolution, but this time stride is 2, and you have 10 as the number of channels, which means you will get something xy y by 10 instead of 10 by 10 by 6. 6 will become 10. But what will this x and y be? This x and y be half of what was the original dimension, because this time stride is 2. So the filter will, instead of jumping 1 unit, it will jump 2 units. So the size will become half of what it was. So instead of 10 by 10, size will become 5 by 5. So this will be 5 by 5 by 10. So you can see that this is 250, 250. I mean, 5 into 5 into 5, there are 250 total number of values. In the original, you had 100 into 4, 400 total number of values in your data. So now a 400 unit representation of your data is now converted into a 250 unit representation of data. So you can see that data is getting transformed as you are applying one convolution after the next. So this is an example of stacked convolution. We can also try to calculate the total number of learnable parameters here. So this filter size is 3 by 3, like that there are 6 filters, but each filter also has a Z dimension of 4, right? Because this 3 by 3 by filter is applied over 4 channels. So you have 3 by 4 filter, but this filter itself, there are 6 such filters. So that's why you have convolution of 3 by 3, 6 such filters. So total number of learnable parameters will be 3 by 3 by 4 by 6. So that will be 9 multiplied by 24. So that will be 240 minus 24, 216, right? 24 multiplied by 9. Yeah, 216. So these many learnable parameters are there in the first filter. In the second one, you have your filter, one individual filter size is 2 by 2 by the 6. So this is one individual filter. Like that, there are total 10 filters. So 2 by 6 multiplied by 10. So this will be 4 multiplied by 6. So this will be 240, right? 6, 24, 240, yeah. So total number of learnable parameters in the first convolution filter stack will be 216. In the second one in the stack will be 240. The total number of learnable parameters here, the sum total will be 456. So this is how you can look at how neural networks use filters to transform the images, but then the filters themselves will learn different features during the training process. Now let's move into the second part of the lecture, pooling. So pooling is very famous. You must have definitely heard of max pooling. So pooling basically reduces the dimension of your data by taking samples of the data. You are pooling samples from the data. One of the most popular pooling technique is called max pooling, where you whatever pixel value is the maximum among a filter set values that come under a filter, then you take the maximum value. For example, let's visualize max pooling here. In this max pooling, let's say your pooling was of 2 by 2, all right, and then you had an image which had a bunch of pixels, and the pixel values are, let's say, this is 1, this is 240, this is 34, and this is 22. Then when this filter is on top of these set of 4 pixels, the result of pooling will be 240, because max pooling will be 240, because you are picking the maximum possible number from the set of pixels. But let's say there is 255 here, then there is 245 here, then when this filter moves from this set of pixels to these set of pixels, now the new maximum value from max pooling is 255. It's not 240. So depending on the spatial location, you are picking the maximum pixel value using max pooling. So this code is another simple implementation of max pooling. So what I'm going to do is, let me just copy paste the code and show you the output, because code is very simple. There is no need to spend a lot of time in the code because the idea is fairly straightforward. Here we are performing max pooling of size, kernel size 2 by 2 and stride 2. And let's just run this to see what we get. We'll be using the same coffee mug image. So you can see that the original image after max pooling, you are picking those pixels whose value are the highest. We can also try changing the stride. Let stride be 1. And if we run this, then the dimension should not change. Maybe let's not define stride here. Let's just define it at the place where we are calling it. So max pooling stride equal to 1. So after changing the stride, let's also try changing the size of the kernel. So right now you don't see much blurring or something like that happening. But let's say the size was 10. Now you will see the image will become a bit blurred. So here you can see that the image has become blurred. But because of max pooling, now it's a 10 by 10 filter, right? So the maximum value that the 10 by 10 filter is seeing is being attributed to that whole region. So you can increase this, by the way. You can increase the size to 100 by 100. Then you will see that this will be even more crazy, the way in which image will look like. See, there are huge regions now that has just one color value, and that one color value depends on the value of the pixel of that particular, the maximum value of the pixel of that particular region that the kernel is seeing. So this is max pooling. Obviously, having a huge pooling size is of no use. But otherwise, if you do max pooling, you can eliminate a little bit of redundancy. You can downsample your data, and this spatial invariance, meaning if you go in X direction or Y direction, the pixel values won't change that much. So the variability in the pixel values will be reduced a little bit. Noise can also be hopefully suppressed, especially if noise is occurring as dark spots. If the noise is occurring as bright spots, it's not a good idea to perform max pooling, because then they will be picked up. So overall, this will reduce the number of parameters required to represent the image. That is what pooling does. Now, just look at this representation of pooling. So here, original image was 8 by 8, and the pooling was of 2 by 2, but here stride is 2. So overall, the dimension of the resulting matrix will be reduced by a factor of half, by a factor of 1 by 2. So totally 8 by 8 will become 4 by 4. Similarly, just let's also look at one more pooling. So for example, if we were having input as 8 by 8, pooling as 2 by 2, but let's say stride, instead of being 2, let's say stride was 1, then the output would be 8 by 8 itself, right? So this is how pooling works. So converting an input 8 by 8 into another output of 8 by 8 is of not that much value, because you have then a lot of repeating values. But here you are converting a bigger image into a smaller dimensional representation. So this is of much higher value. Now let's get into the last part of today's lecture, AlexNet. So we will look at AlexNet, and we'll also implement it for the 5 flowers dataset. So AlexNet is a legendary deep neural network architecture that completely changed computer vision. This was introduced in 2012 in a paper. So if you Google AlexNet paper, Google Scholar, most likely, yeah. So this is the Alex who's behind AlexNet. His surname, I don't think I can pronounce it in the right way, but this paper overall has 170,000 plus citations. You just look at some of the other names that are part of the AlexNet paper. Ilya Sutskever, he was part of OpenAI. Then you have Geoffrey Hinton. Geoffrey Hinton is the 2024 Nobel laureate in physics. He is this professor, Geoffrey Hinton. And then Ilya. Ilya is also now very famous because of his role that he played in OpenAI. But basically, this paper, what it accomplished is it showed for the first time that you can use deeper neural network that involves convolution, that involves ReLU, etc., to perform very well on image data sets. So there was this ImageNet competition going on for whoever can accomplish the best test accuracy in the ImageNet competition. That was such a big deal. It was a very prestigious competition to be part of if you were working in deep learning at that point of time. And AlexNet completely, I would say, killed all the other competitors by a very good margin. So AlexNet was this architecture. So it involved a bunch of convolution layers. It involved max pooling. It involved ReLU activation. So you can see that if you had an input image, so let's say 224 by 224 by 3. So this is the flower data set. Then you had a convolution operation of 11 by 11 by 96. So this was, and then there was a ReLU, then another convolution 5 by 5 by 256, another ReLU, then max pooling. Like that, there were several set of convolution stacks. And here stride is also defined: stride 4, stride 2, stride 2, etc. We will come to how to calculate how the image dimension kind of transforms through different layers. We will do that in a bit. But let's also look at the total number of parameters. So totally there are around 62 million parameters in this AlexNet. Can we now try to calculate how exactly we arrive at this number? So let's see, right? This will be an interesting exercise. So in the first convolution layer, you have 11 by 11 by 96. All right. So 11 by 11 by 96 means let's multiply 11 by 11 by 96. So that is 11,616. That is the number of learnable parameter, 11,616. Then here you have 5 by 5 by 256. So that will be 6,400. These many number of learnable parameters. And the number of learnable parameters will also depend on the image dimension. So here the original image dimension, it has 3 channels instead of just 1 channel. So you also have to multiply this by 3. So 11,616 multiplied by 3 will be 34,848. So multiplied by 3 equal to 34,848, correct? And this will be 6,400 multiplied by 3. No, 6,400 multiplied by the dimension of the previous image. The previous one had dimension to be 96. So 6,400 multiplied by 96, that will be 614,400. 614,400. So here you can see convolution layer 1 has 34,944. Convolution layer 2 has 614,656. I think this is because we have not counted the bias. We are only counting weights. So what we can do is and these are just weights. For bias, we need to add, let's say, whatever is the image size, we have to add that also as the bias. So we will have 11 by 11 by 96 added on top of, not 11 by 11 by 96. It will be 11 by 11 by 3, I guess. Let's calculate 11 by 11 by 3. This is 363. So 34848 plus 363 will be 35221. Is that what we have? No, it's 34944. I would say a better way to calculate would be using Google Sheets. So what we can do is let us put layer by layer the number of weight parameters and number of bias parameters, and then let's do the math here. So first, layer 1. In layer 1, let's put it here. Then first, we are looking for weights, bias, and total. So number of weight parameters in the first layer is 11 by 11 by 96 equal to 11 by 11 by 96. So that is 11,616. But then this is multiplied by 3 because you have 3 channels in the input image, not just one channel. So you can multiply this by 3. So this is the total number of weight parameters. Now the number of bias parameters will depend on the 96 because you have total 96 as you have total 96 dimensions in the final output. So because your convolution size is 11 by 11 by 3, but your final output is 96 dimension. So then total will be equal to this plus 96. So these many number of trainable parameters. In layer 2, you have 5 by 5 by 256. So equal to 5 into 5 into 256. But then the previous layer actually had 96 dimensions, right? So you have to multiply this by 96. But the current layer output has 256 dimensions. So this will be 256. And the total will be equal to this plus this. So 614,656. Is that what it is? Yeah, that is correct. Now in layer 3, you have, this is an interesting exercise. You may skip this also, but I think this is fairly interesting to perform. In the next convolution layer, you have 3 by 3 by 384. So 3 into 3 into 384. But this has to be multiplied by the dimension of the previous layer. The previous layer had a dimension of 256. So you're multiplying by 256. Let me check if it is 880,000 or not. Something like that. Yeah, it is. And this total number of bias will be total number of output dimensions here, which is 384. So 384. And then output will be same as this formula, 885120. Is that correct? That is also correct. So like this, you can calculate for every single layer how many number of learnable parameters are there. And in AlexNet, there are total around 62 million trainable parameters. So it's like a huge neural network. And these many trainable parameters also involve stacks of different convolutions. So you have there are 5 convolution layers. In between, there is max pooling. There is also ReLU activation. Some max pooling have stride 2. Then you have finally 3 fully connected layers. And at the very end, you have softmax for probability distribution. This fully connected layer dimension will depend on number of classes. So here it was showing 1000 classes. In our case, we will need 5 classes. So you can attach one more fully connected layer with just 5 nodes and ReLU activation in the previous layer and softmax in the very last layer. So this will be the structure of the AlexNet. Now, if you want to implement AlexNet using Keras, you can do that. But the only downside is that we can't implement transfer learning. Keras does not have a pre-trained AlexNet readily available. You can get AlexNet from PyTorch and convert it into like a TensorFlow format. And then you can use Keras to access that. But that will be a difficult business. So in today's lecture, we are in fact going to be using PyTorch instead of TensorFlow Keras. Okay, but I will anyway show you if you were to implement AlexNet completely from scratch using Keras. It's very simple. You just need to add different layers as models.sequential, and the exact same layers that we have mentioned above, you can simply add. So here I have added input shape of the image 227 by 227 by 3. Then you have 11 by 11 kernel of 96 dimension, and stride in the first 11 by 11, the stride size is 4. So here that also is mentioned, stride equal to 4. Like that, you add different layers, and overall, this is the structure of the AlexNet. But this is useless for us because, as we have seen in the previous lecture, training a neural network, especially deep neural network from scratch, is a waste of our time, because there are already so many pre-trained neural networks available which can perform very well and which can hopefully give us much better accuracy. So today we want to use pre-trained AlexNet. So we are now going to be switching to PyTorch instead of TensorFlow. Pretty much the same thing. If you want to learn more about PyTorch, I'll just put a simple introductory video about PyTorch. It's a framework for deep learning models. And PyTorch is considered to be more advanced. But since the problem statement that we are looking at today is very simple, today you will not find any difficulty switching from TensorFlow to PyTorch. I'll be anyway sharing all the code with you. So I think you will find it fairly straightforward. But this is the model summary. If you were to run this code, AlexNet summary, in fact, let me just show you by running this code. It will print the model summary and you will see the 62 million parameters that being displayed in the AlexNet.summary. And if you want to remove some layers, you can do that. You can have a modified AlexNet with less number of trainable parameters. But the original AlexNet had around 60 million, and that is exactly what we have, around 62 million. All right. So now let's also discuss a little bit, why is AlexNet such a big deal? What exactly did it accomplish in the realm of deep learning or in the realm of computer vision? So in the ImageNet challenge, so ImageNet you can find from Google, just Google ImageNet and you will find the data set. It has several million annotated data sets split into various label data formats. There are 1,000 label data set. I think there are also 20,000 label data sets also. But I think the original ImageNet challenge had a certain number of images in the training category. Validation, you can split yourself. And for the testing, they will have some image data set which will not be exposed to you. And then they'll be testing on their test data set how well your model is performed. And in 2012, what AlexNet did is it won the ImageNet challenge by a huge margin. And this truly opened the deep learning revolution, because before this, people were looking at deep learning just as a research topic. Researchers were interested, but not people from serious computer vision backgrounds. Industry was not considering deep learning. But AlexNet showed that deep learning can, in fact, outperform feature engineered machine learning models. And it can eliminate the need for even engineering the features, because in an image, you are not engineering the features. Your pixels are the values which you keep as such, and you let the neural network teach what the convolutional filter parameters should be. You are not manually engineering them. One more thing AlexNet accomplished is it showed that you can use GPU for training, which can significantly accelerate. This is also the time when GPU revolution started to happen in the context of AI. Until then, GPU was primarily used for gaming, like rendering graphics. So NVIDIA's GPU at that time, some of you who may be into gaming, you might be familiar with how you could purchase a GPU for 5,000, 6,000 rupees, and you can have a better gaming experience. But now most of the GPU industrial purposes are for accelerating AI model training. And in the same AlexNet model, they introduced ReLU instead of sigmoid. So ReLU is unbounded, meaning for all positive numbers, ReLU of x is equal to x. So it's an unbounded function. So faster training was possible because gradient of that ReLU function is 1, irrespective of the value of x. Then you have, there was dropout regularization introduced for preventing overfitting. So some nodes in the output layers, I mean, in the hidden layers were switched off at random. Then there was max pooling. Then there was data augmentation using random cropping, rotation, etc. So all of this allowed AlexNet model to perform much better than their contemporary models. And this is when truly deep learning took over computer vision. So today in the first part of the lecture, we were manually defining some filters, right? That was not needed anymore because filters were converted to learnable parameters. And this happened primarily because of the revolution brought by AlexNet. So AlexNet, you can think of AlexNet as the most important paper in the history of computer vision, because it completely changed the way people tried to process images using a computer. So now let's implement AlexNet for our 5 flowers dataset images. So before we implement, I'm directly first going to show you the results because I'm so happy and I don't have the patience to wait until the end of implementation for you to see the results. The results are the best that we have accomplished so far in this course. So this dotted line is the training accuracy and this blue line is the validation accuracy. The training accuracy was close to 90-95% and validation accuracy was almost 90%. We have never ever accomplished 90% validation accuracy with any method so far, but now AlexNet has accomplished that. But there is a small caveat. There are minor differences in the dataset that we have used. Yes, it is 5 flowers dataset, but 2 of the flowers are different because this time we are implementing AlexNet using PyTorch. And for PyTorch, you require dataset in a certain format. So let me first show you the code. So this is the code. And what I did is this time I loaded the dataset in my Google Drive. So let me first connect my Google Drive by running this piece of code, and I will show you how the dataset structure is. And this will create a pop-up asking you to connect your Google Colab with your Google Drive, which is fairly straightforward, nothing fancy. Yeah, so connect to Google Drive. And once you connect to Google Drive, your Google Drive folders will appear over here. And in those folders, I just want to show you the structure of our dataset. So this is how the folder looks like. So what I did is I downloaded the dataset from Kaggle, but dataset just had one folder. In the one folder, there were 5 subfolders: lily, lotus, orchid, sunflower, tulips. If you remember from our original 5 flowers dataset, lily was not there and lotus was also not there. I think it was dandelions and daisy. But instead here we have lily and lotus. That is fine, no problem. But here there are total 5,000 images. Each category of flower has 1,000 images. Then we had to split that into training and testing. So what I did is I ran a Python code, which was easy to generate. But I used the Python code to split the training, split the total dataset into 80% for training and 20% for test validation. So the 20% dataset of 200 images each is in these 5 folders. The remaining 80% for training are in these 5 folders. And this whole folder called 5 flowers data is now in my Google Drive. I will also share a link to this folder so that you can get the dataset directly. You can download it from my Google Drive, or you can directly take it to your Google Drive and you can operate, you can perform training of the model on top of that. So this is the data set, and then these are the parameters, I mean hyperparameters that I'm using. 10 epochs, batch size 16, learning rate 0.001, and model architecture is AlexNet, but I'm using pre-trained AlexNet, and input image size is 128. This is what we used in the previous lecture also for transfer learning. I think the only difference was learning rate in the last lecture was 0.0001, 10 to the minus 4. But here it's 10 to the power of minus 3. And this is stored as a weights and biases configuration. And when we are running the code, obviously, this will ask you a weights and bias, this API key. So you can find the API key over here. When you create a weights and bias account, I have already made a detailed lecture on this topic. So that's why I'm going a bit fast about the weights and biases. First of all, weights and biases platform is just used for logging your results. It's not necessary to use it. You can directly run the code without weights and biases, so that the results are directly here in the Google Colab. But instead, I wanted to store the history of all of my experiments in a nice way. So here you can see the different experiments that I have been running throughout this course. So all these experiments are nicely stored here. I don't have to worry about where are my results, right? So that's the only reason why I'm using weights and biases. Then data pre-processing, like normalizing the data, resizing, etc. But the only thing you have to change is, in my case, this is the training data folder. So I have to click on these 3 dots, copy path, and I have to paste the path here. Similarly, for validation, also copy path and paste in the validation directory, and then run the rest of the code. So you have to just be careful that you are giving the appropriate path here for according to your folder naming convention. And then you can run the rest of the code. But basically, just notice what we are doing here. In the AlexNet, we are defining a final classifier layer, AlexNet.classifier of 6. And that is a layer with 5 output nodes, right? Because we are performing a 5-class classification. That is the main thing. And let's run this code. This part is also easy. Then cross entropy loss is what we are using. Optimizer will be Adam. And learning rate we have already configured in our weights and biases configuration to be 0.001. And we are running for 10 epochs. So this execution will take some time. Rest of the code are fairly straightforward. We have already spent enough time on this in the past lectures. But basically, the only difference is, since we are running in PyTorch, we are not building keras.sequential. We are not building layers in that format, but rather we are using this one. We are using the loss object, and from this object we are calling the backward pass function. From optimizer object we are calling the step function, taking one step in the optimization process. So here in PyTorch, many of the neural network functions and neural network operations are defined inside classes. So we define objects to create instances of those classes, and using those objects only we call the required functions. In our Keras, it was much more simpler. It was just a sequential function in which we had to add each layer. But here it's a little bit different if we wanted to add more layers. But the code itself is fairly straightforward, and I will be sharing that with you. But here you can see that running the code is already one batch has started. Like this, it can progress. One more thing is in the runtime type, here I'm using T4 GPU, which is available for free. You don't have to pay anything. So I think this will speed up your computation a little bit. By default, it will be CPU, so you can change it to TPU. So all you need to do is like click this arrow, then change runtime type. I'm not going to click it right now because that will kind of interrupt my execution. But you click this, and then instead of CPU, select T4 GPU. And then as the epochs are getting executed, your data will be stored here. So this is the experiment which I ran yesterday, and I will show you the results in the form of the graph. Plotting is also fairly straightforward here, but basically this, yeah, I think it is. I just need to find the right experiment which I performed yesterday. Yeah, I think it is this one only. I can add the data plot here by simply plotting epochs on the x-axis, and on y-axis I want training accuracy and validation accuracy. So val accuracy. So this is basically the plot. The first plot has around 90. 0.83. No, this was not the plot that I had yesterday. The plot that I had yesterday after finishing my experiments was after 10 epochs, I had around 93-94% training accuracy and close to 90% validation accuracy, the highest that I have ever obtained in any experiment. So this is what I managed to obtain with the hyperparameters that I was using. I could, of course, do a little bit of hyperparameter tuning and probably take the accuracy closer to maybe 95%, etc. But I will leave that to you. But this was a great exercise using an already existing famous neural network architecture for our purpose and getting some meaningful result. And in the next lectures, we will see how to improve this even further. We'll be using VGG. We'll be using other deep learning architectures that are very famous, which came after AlexNet. So AlexNet started it. It doesn't mean that AlexNet is the best deep learning architecture out there. There are even better ones. So we'll be using that in the next lecture. But with that, we can wind up today's lecture. But let me spend just half of a minute congratulating you for coming all the way till this part of the course. This is a very rigorous course, but I'm sure that you are learning a lot. And if you are implementing all of this code along with going through the lecture, I'm pretty sure you are gaining hands-on experience also. So our journey has been fascinating, right? We started with a linear model. We added one hidden layer. We played a little bit with the hidden layer hyperparameters. We then introduced, and in the hidden layer, we also had nonlinear ReLU activation function. Then after that, we introduced normalization, batch normalization, dropout, regularization, etc. Then we saw that, oh, the validation accuracy is just 55-60%, not more than that. Then we realized that we have to do transfer learning. In the last lecture, we used ResNet 50 for transfer learning. It was pre-trained on ImageNet dataset, and that performed really well. We had 83% validation accuracy. And today we use AlexNet, and we used again a pre-trained AlexNet. And now here we have 90% validation accuracy. And in the next models that we are going to try, this is only going to improve. So you must feel very relieved and very happy right now that you are having some meaningful results. But with that, thank you for staying with me. I'll be looking forward to seeing you again in the next lecture. Take care until then. But more importantly, be very proud of yourself for being part of this journey until this point, because a majority of the people usually drops out by this time, because it's very difficult for people to keep coming back and learning the material lecture after lecture. So if you are watching this right now, I think you have already done a fantastic job. So see you soon. Take care.